Hello, everybody. Welcome back. We're going to be talking about networks for pretty much the remainder. This will encompass the remainder of the new material in the course, which is really exciting because now you know that there's only one thing left to learn, and it's really interesting and fun, I think. So we're going to dive right into it. I hope that podcast episode served as a pretty good introduction to the concept of networks and how they gave rise to the concept of 6 degrees of separation, the idea that on average, or the idea that people around the world are separated by no more than 6 degrees. Like, you know someone, they know someone else, they know someone else, no more than 6 times to get to every single person. And this is an idea that has kind of propagated throughout all of popular culture. There was a movie about it, and there's a track by Ghostface Killah called 6 Degrees of Separation, featuring Danny Brown. So it's really everywhere. And that whole idea comes entirely from theory about networks. So what I'm going to talk about today is how to translate between a network diagram and a network matrix. So I'll talk about what those are shortly, but let's just start off with an example, a very, very simple example of a network. So let's have these 3 nodes. Let's call them node 1 and node 2 and node 3. So nodes are one of the 2 major pieces. So I'll write those over here. So the 2 things that make up networks are nodes and then edges. So these will be our nodes, and then let's say that we have 2 edges. We have an edge connecting. Ooh, ugly. Oh, there we go. That's better. So we have a edge between 2 and 1, node 2 and 1, and an edge between 1 and 3. And let's say that that's it. That's all we have for. So 3 and 2 are not directly connected. So this is the most probably the clearest way to represent a network is with this picture. And so I'll call this the diagram because it's just a network diagram. And then next we'll have the network matrix over here. So a matrix is a more compact way to represent what's being shown in the diagram. And so the way this would work is you have a 3 by 3 grid, or in general an n by n grid. If this has 3 nodes, so this matrix is going to be 3 by 3, but if it had any number of nodes, this would be if it had n nodes, then this would be an n by n matrix. N nodes. And the way this 3 by 3 matrix works is that each column will represent a matrix, and each row will represent, each column will represent a node, and each row will represent a node. And then the numbers in the entries will represent whether or not 2 nodes are connected. So let's go ahead and do, let's use a pen that works, first of all. That might be a good starting point. Let's say we have node 1, node 2, and node 3. Those are the 3 columns. And then we also have a row. Node 1 has a row, and node 2 has a row, and node 3 also has a row. Okay, and now each entry, so there are there are 3 times 3 entries in this matrix, so there are 9 entries, and each entry represents whether or not 2 nodes are connected. So we're going to start off with 1, this 1 column, and go through the rows and look at which rows it is connected to. So for 1, we'll say, okay, it's connected to itself because every node is always connected to itself. And it's connected to 2 via this edge right here. So that's also a 1. And it's also connected to 3 because of this edge. So this is a 1. But if we move to 2, it's connected to 1 because of this connection here. It's connected to itself, it's connected to 2, because by definition we say that nodes are connected to themselves. But it's not connected directly to 3. So this will be a 0. And then going through 3, 3 is connected to 1, so we'll call this a 1. So this entry will be a 1. 3 is not connected to 2, or at least not directly. You'd have to go through 1 to get to 2. So that's a 0, and then it's connected to itself because all nodes are connected to themselves. And this is what we get for our matrix, our network matrix in this case. And you can have either one of these and be able to draw the other, or be able to write the other. Both of them give you maximal information. The diagram is a little bit better at conveying what's going on to a human brain. You see that and you go, okay, I see what's going on. This is a little bit more obscure, but it's more compact. So essentially what's going on here is, I call it a matrix, but really it's a table. It's a table with columns and rows, just like all the other tables that I have you fill out in this class. But the reason that we call it a matrix instead of a table here are 1, because it sounds cooler, and 2, because when network theory gets more advanced, you start doing operations on matrices that are specific to them that you can't do to just a table. It has to be the mathematical object of a matrix. And also, sometimes these can get really big and it will become clunky to have all these labeled columns and rows and stuff. So it's a matrix, and you're in the matrix now. So, get over it. One thing that I want you to notice here is that this matrix is symmetric. And what that means is that if you look at just the lower, this is our diagonal. The diagonal is defined by the entries whose row and column is the same. So 1 and 1, 2 and 2, 3 and 3. So if you look across the diagonal, this half is the same as that half. They're mirror images of one another. So that's what this would look like as a. This matrix is symmetric because this is an undirected network. And so networks can also be directed, and so I'll talk about that next. So I'm going to erase these entries now. Let's pretend that instead of these just being kind of general just connections, these vertices, let's say that they're directed vertices. So let's say that this is connected to, so 1 is connected to 2 in this direction, but 2 is not connected to 1. And then let's say that 1 is connected to 3, and 3 is connected to 1, like that. So this is a dually directional vertex, or edge, and see if this one works this time. And let's say that 3 is connected to 2, but also not vice versa. So we only have we only have this direction for that edge. Okay, so now what's going to happen is as we fill out this matrix, we're going to put down a 1. We're going to go through 1, and we're going to put down a 1 wherever 1 is connected to the corresponding node. So 1 is still connected to itself, so that's still true. And 1 is connected to 2 because we have a connection to 2. It's going to 2 like that. So we'll put a 1 there, and it's also connected to 3 because there's an arrow going from 1 to 3. Now for 2, it's actually not connected to 1 because there is no arrow going from 2 to 1. There's an arrow going from 1 to 2, but not in the other direction. So this is actually a 0. And then 2 is connected to itself, sure. And then 2 is not connected to 3 either because there's no arrow going from 2 to 3. So this is also 0. And then for 3, we have that 3 is connected to 1, and 3 is connected to itself, and 3 is connected to 2. And so here we have a slightly different pattern that we wouldn't have gotten in an undirected matrix. So if you're doing, so I'm just going to put some more notes on the side here about this. So network type. And matrix. So if it's undirected, your matrix is symmetric. And if it's directed, then it's not symmetric. And so now there's one last variation of the network matrix duality that I want to talk about for this, and then after that we'll be done. We can go into class and work through examples because this is a lot to remember probably right now. So I'm going to go back to the undirected picture, but now I'm going to give the edges weight. So okay, so now let's say that let's give the connection from 1 to 2, let's give that a weight of 3, and let's give the connection from 1 to 3, let's give that a weight of 4. Okay, and so this weighted networks are usually representations of some sort of system where the connection between two things has some sort of cost, and so these things usually represent a cost or a distance. Sometimes it's the distance of the connection, but usually the higher the number, the weaker the connection is, because it's like they're further away, or it costs more to get from one to the other, that kind of thing. The way we translate this into the matrix is the exact same way we did for the original undirected matrix, except we use these numbers as opposed to just ones and zeros. So we'll still use 0 for no connection, but then we'll use the 3 and the 4 for a connection of each of those weights. So, and then we'll leave the connections, the nodes that are connected to themselves, we'll just leave as 1 by convention. That doesn't really mean too much. So let's have so 1 is connected to itself with a weight of 1, but it's connected to 2 with a weight of 3, and it's connected to 3 with a weight of 4. Then 2 is connected to 1 with a weight of 3. It's connected to itself with a weight of 1, and it's not connected to 3, so we go to 0. And then 3 is connected to 1 with a weight of 4, and it's not connected to 2, and it's connected to itself with a weight of 1. So that's how we'll end up when we want to convert a weighted network into its matrix. And then if we could also have a, oh yeah, so I'm going to put this over here first. So I'll start first unweighted. So these are the matrix that we had. So the two examples that we did before this one were unweighted networks. And so unweighted, we have just 1s and 0s. And then weighted, you can have any number in your matrix. Well, any positive number. And then one thing that I want to mention, although I won't go through an example of it right now, is that if we could also have a weighted directed network, in which case we would treat it the exact same way as we treated the directed network, where we would do the same process, but pay attention to the arrowheads as well. So you might have something like this, that. And if you wanted to attempt to convert this into a matrix, that would be a good exercise to see if you could extrapolate from the previous 3 examples how to get this into its matrix form. But we'll do a lot of practice with this. So if that is confusing, it likely is. Don't worry about it too much. This mostly just serves as the foundation, and we'll get a really good handle on this during class on Tuesday. If you have not yet listened to the podcast, definitely do that. It's very, very nutritious, and it, I think, helps a lot with the interpretation of these networks. So you should definitely do that. Do the self-quiz, and everything will be great. I'll see you on Tuesday.